As you may have guessed, we will be using search to solve STN planning problems. The search nodes in the search space that we'll be searching will be task networks. And the methods we have just described will be used as refinement operations in our new search space. Methods give us the state transitions we need to move from one task network to another. And the way this is done is that we use methods to decompose tasks, and that's what I'll be talking about next. Here is an example how decomposition works in the dogwalker robot domain. And to do the decomposition, I've already introduced the decomposition function delta that takes a task, a method instance, and a substitution sigma. We can visualize the process of decomposition by means of a decomposition tree, which is what you see here. The decomposition tree has as its root the task T, so this is the task T that we're trying to decompose, and that is the root of our decomposition tree. In this case, the task was to move the stack from P1 to some other pile Q. Then we have a method instance that we're using to decompose the task with, and the method instance here is recursive move P1, P2, C1, C2. And the final component, the substitution sigma, tells us how we have to replace the variables. So that's what we find here. We have to replace the variable Q with the value P2. Then the children that we have of the node that represents the task that we're trying to decompose are exactly those subtasks that we find in the method. So here it is the first subtask move topmost and the second one to move the stack. The only other thing worth noting is this arrow here that underlines the substitution and the method, and that simply gives us the order in which we have to execute the subtasks. And if we look at this tree, we can immediately see what the result is by looking at the leaf nodes. So this is the result of this decomposition here, namely to move the topmost container from pile P1 to pile P2, and then move the remaining stack from pile P1 to pile P2. As you can see, there's quite a lot of redundant information in this tree. For example, you can derive the substitution you're looking at from the values used in the task and the method, or in the subtasks. That is why when you see this tree later in another example, I will leave out some of that information to save a little space and to be able to draw bigger trees. Now that we understand how to decompose a single task in isolation, we will look at how to decompose tasks that are in a task network. So we start with the task network W consisting of nodes and edges, where the nodes are tasks and the edges are ordering constraints. And we want to decompose one of the tasks T that is in this network, and this must be a task that has no predecessors in W. So if this network is totally ordered, then it will be the first task in the list. If it's a partial order network, there may be several tasks that have no predecessors. Then we want to decompose this task using a method, and this method of course has to be relevant for the task under some substitution sigma. And this method itself will have a network consisting of nodes and edges. Then we can define the decomposition of T, the task T, in the network W by method M under our substitution sigma as follows. The first thing we have to do is we replace our task T by the instantiated network tasks that come from our method. So from our original network W, consisting of the tasks in U, we remove the task T, and in its place we put all those tasks that are in UM and instantiate those with the substitution sigma. That is how we modify the tasks in the network, and then we also have to modify the edges in the network. And the edges we have to replace are exactly those edges in E that involve T, because T is no longer available as an endpoint to an edge. We have to replace them by edges to appropriate nodes in our new set of nodes that we've just introduced, sigma of UM. To illustrate this, let us look at a simple network that consists of two task nodes that I illustrate here, and just one edge that orders these. Let this be our network W. Then The only task that has no predecessors here is this task here, and that's the one we can decompose now. And suppose we have a method that is also very simple and decomposes our task into another very simple network, just like the one above, consisting of nodes 1 and 2, let's say. Then the first thing our decomposition function does is replace the task t, so we have to remove it from the network, and we insert the subtasks defined by the method. And these are, of course, the tasks 1 and 2 from our method. And then we have to replace all the edges that were connected to t, which is this edge here. And we can replace this with edges to all the newly introduced nodes. So we have to have an edge here and an edge here. But because we already have this edge, there's no need to have the second edge. So we can actually omit that if we wanted to. And in this example, the resulting network would be the sequence consisting of the node 1, 2, and this final node here, which I'll call 3. And what we have done to get to this network is we have applied the decomposition function, which is defined here. And the application consisted of 2 steps. We have replaced the node t that we're decomposing by all the nodes in the network of the method. And we have replaced all the edges that are connected to t by edges to the new node. And this is how you decompose a task in a task network.